This illustration helps demystify the transformer. First, let's visualize it as a single black box transforming one language into another.
So we feed it a sentence, and out comes its translation. That's the high-level function, like any neural machine translation system.
But when we pop it open, we see two major parts: an encoding component, a decoding component, and connections between them. This structure is typical for sequence-to-sequence models.
Right. The encoder processes the input sentence, and the decoder generates the output translation. That makes sense for language tasks.
Each component isn't just one layer, it's a stack of encoders. Think of them as multiple processing stages, each refining the input representation, similar to how a deep neural network learns progressively complex features. However, unlike some networks where each layer might have a completely different architecture, these stacked encoders maintain the same fundamental structure, applying self-attention and feed-forward networks repeatedly.
Like a deep neural network where each layer learns increasingly complex features. But what's inside each of these individual encoders?
Each encoder's input first flows through a self-attention layer and then through a feed-forward network. This self-attention is key.
Self-attention. Is that different from the attention we discussed in case number TCM 123005, where an RNN would focus on parts of the input during decoding?
It is. Here, self-attention means the layer helps the encoder look at other words in the input sentence as it encodes a specific word. The self implies it's attending to its own input sequence.
So as it processes animal, it can look back at the? Or is it looking back at animal?
Exactly. Consider the sentence, "The animal didn't cross the street because it was too tired." When the model is processing the word it, self-attention allows it to associate it with animal.
That's a classic ambiguity problem. Without self-attention, it might only have its own embedding, not the context of animal or street.
That's the core idea. Self-attention is the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing. This baking isn't literal. It's a weighted sum of information from other words, creating richer, context-aware representations for each word.
So each word's representation isn't just static. It's dynamically informed by its entire context within the sentence.
If you're familiar with RNNs, their hidden state allows an RNN to incorporate its representation of previous words. Self-attention does something similar, but in a parallelizable way.
The parallelization is the key distinction. An RNN builds understanding sequentially, but self-attention forms these connections all at once.
Wait, if self-attention processes words in parallel, does it care about their order at all? Like, if I rearrange the words in a sentence, would the self-attention layer give the same output?
That's a crucial observation, Maya. Self-attention layers are inherently permutation invariant. They treat all words in the input as a set, without inherent regard for their position. This is great for parallelization, but problematic for language, where word order is vital for meaning.
To solve this, we must inject some information about the relative or absolute position of the tokens in the sequence. This is done by adding positional encodings to the word embeddings before they enter the transformer. These are mathematical patterns that tell the model where each word sits in the sequence.
So each word gets its meaning from the embedding, and then its position from the positional encoding, and these two pieces of information are combined? That makes sense. It's like giving each word a GPS coordinate in the sentence.
Right. One subtle point. After self-attention, the exact same feed-forward network is independently applied to each position. There's no dependency across positions in this step, unlike self-attention.
So the complex contextual interaction happens in self-attention,
and then each position gets a standard independent processing step. That clarifies the workflow.
This high-level view is useful, but the core innovation lies in how self-attention actually computes these relationships. Let's get into the mechanics.
Okay, so how do we take words, turn them into vectors, and then use those vectors to calculate these baked-in understandings that self-attention provides?
Let's break down this self-attention calculation. It starts with word embeddings, which are vectors representing each word. From these, we create three crucial vectors.
We've seen embeddings before, so each word enters as a numerical representation. What are these three vectors?
For each word, we create a query vector, a key vector, and a value vector. These are derived by multiplying the word's embedding by three learned weight matrices.
Query, key, value. That sounds like a database lookup. Is that a good analogy here?
It's a very helpful abstraction. They're abstractions that are useful for calculating and thinking about attention. Think of the query as what you're looking for, the key as what's available to be matched, and the value as what you'll retrieve.
So my query for it would find the key for animal, and then I'd retrieve a value associated with animal? That begins to make sense.
The next step is to calculate a score. This score is calculated by taking the dot product of the query vector with the key vector of the respective word we are scoring.
Dot product measures similarity. So a high dot product between query it and key animal means they are very similar, suggesting relevance.
Precisely. The score determines how much focus to place on other parts of the input sentence. It's a raw measure of how much one word's context should influence another's.
Okay, so I get scores for it against every other word, the, animal, didn't, etc. What happens to these scores?
We first divide the scores by 8, specifically by the square root of the dimension of the key vectors, which was 64 in the original paper, making the divisor 8. This scaling helps stabilize gradients during training, preventing very large dot products from dominating. Then we pass the result through a softmax operation. Softmax normalizes the scores so they are all positive and add up to 1, turning them into a probability distribution.
This gives me a probability distribution. Now I have clear weights, telling me exactly how much each word should attend to every other word.
This softmax score determines how much each word will be expressed at this position. It's like a learned interpolation weight. Case number TCM123005 said attention is just lookup, but here we see it's more like learned interpolation.
I like learned interpolation. It's blending information, not just pointing. So what exactly gets blended?
Now, we multiply each value vector by its corresponding softmax score. The intuition here is to keep intact the information from the words we want to focus on, those with high scores, and effectively drown out irrelevant words by multiplying their values by tiny numbers. Finally, we sum up these weighted value vectors. This produces the output vector for the current word, which is a new, contextually enriched representation incorporating information from all other words based on their attention scores.
So that single output vector for it now contains weighted information from animal, street, and every other word. It's a dense, context-rich representation.
Exactly. And transformers don't just do this once. They do multi-headed attention. Instead of one set of query key value projections, the model creates several. Each head learns to focus on different aspects of the relationships between words.
Multiple perspectives on the same sentence. So one head might focus on grammatical dependencies, another on semantic relationships like it and animal.
Precisely. The transformer linearly projects the queries, keys, and values h times with different learned linear projections to h different lower dimensional q, k, v sets. Then, on each of these, we then apply the attention function in parallel, yielding h output values. Finally, these are then concatenated and once again linearly projected to yield the final values, which combine all those rich perspectives.
Wow, so instead of one big contextual vector, each word gets a supervector, a combination of multiple nuanced contextual understandings. That dramatically increases its expressive power.
We've seen how the transformer revolutionized natural language processing, but its true versatility became apparent when researchers realized its sequence processing power wasn't limited to text. It could handle images too.
Images? How do you apply something designed for sequences of words to a two-dimensional grid of pixels? That seems like a massive leap.
The core insight was elegant in its simplicity. An image is split into fixed-size patches, each of which is linearly embedded and fed as a sequence of tokens to a standard transformer encoder. Essentially, an image becomes a long sentence of visual words.
So a 16 by 16 pixel patch becomes a token, like a word, and then the transformer sees a sequence of these visual tokens, just as it sees a sequence of word tokens.
Exactly. And just as with text, because the transformer's self-attention is permutation invariant, positional embeddings are added to the patch embeddings to retain positional information. This allows the model to understand where each patch is located within the image.
That's brilliant. It abstracts images into a sequence format the transformer already understands. So self-attention on visual patches helps it see relationships between different parts of an image, no matter how far apart they are?
The transformer's ability to model global context effectively, learned through self-attention, is key to its success in vision. Unlike convolutional networks, which process local regions and build up global understanding hierarchically, a vision transformer can relate any two patches directly, regardless of their distance. So it could instantly connect a dog's ear to its tail, even if they're far apart in the image, without needing many layers of convolutions to bridge the gap. That's a powerful new way to see images. Indeed, this flexibility is powerful, but it also reveals some inherent trade-offs. One significant limitation of the original transformer's self-attention is its computational cost. If your sequence length is L, the self-attention mechanism has a quadratic complexity, meaning it scales as L squared.
Quadratic? So doubling the length of the sequence, say from 500 words to 1,000, quadruples the computation? For very long texts or high-resolution images with many patches, that could become prohibitive very quickly.
Precisely. This quadratic complexity makes it less efficient for extremely long sequences. Furthermore, while CNNs have an inductive bias for local features, they are designed to look for patterns in small adjacent regions. Transformers lack this. They are more general purpose, but often need much more data to learn these local relationships from scratch.
So the attention is all you need approach is powerful and universal, but it's not a silver bullet. It excels with enough data and when global context is important. But its computational cost and lack of built-in local priors mean it has its own set of challenges. It sounds like a new architectural frontier with its own landscape of optimizations and variants.
Exactly. From transforming languages to recognizing images, the transformer's elegant self-attention mechanism has proven to be a foundational architectural breakthrough, sparking an entire generation of research and applications. It truly reshaped how we approach sequence modeling across diverse domains.
And the journey continues, with new variants constantly pushing the boundaries of what this architecture can achieve. Thanks, Arjun.